All right, today we're going to be working on 3.6, one-to-one functions and inverse functions. So the objectives for today are really understand what a one-to-one function is, determine if a function is one-to-one using a horizontal line test, understanding and verifying inverse functions, sketching the graph of inverse functions, finding the inverse of a one-to-one function. So that's what we're going to be working on today. So what is a one-to-one function? Well, first, it's a function. So because it's a function, we know that for every x, there has to be only one y. So we start with, for every x, there's only one, or exactly one y value, okay? But we never talked about the opposite. Like for every y value, there's only one x value. And that's what we'll be talking about with one-to-one functions. Now we're really looking at if you have a function, then what's happening? Can you have more than one x value for one y value? And that's basically what this definition says. A function f is one-to-one if for any values where a is not equal to b, or basically they're saying there's two different x values, then those have to align with two different y values, okay? And that's not what we've been talking about with a function. We've been talking about it the opposite way. Let's see. Alternate definition of a one-to-one function. A function is one-to-one if for any two range values, f of u and f of v, if they're equal, that means that u and v are equal. I'm not sure if either one of those definitions is as understandable as I'd like for them to be, but basically, what we're going to talk about is we have a vertical line test for functions, because if you make a vertical line, then if you have an x with two y values, you'll see it. For one-to-one functions, of course, you have to pass the function test, and then we're going to see a horizontal line test where if you have two y values if you have one y value and two different x values, then that means that it's not one-to-one. So for example, this is a one-to-one function over here on the left. It's x cubed, it's one-to-one. It's a function because it passes the vertical line test. And also it would pass a horizontal line test. For every value of a, for every value of y, there's only one x, and for every value of x, there's only one y. That's not true here, okay? So what this is saying is that we have two different values of x here, and they equal the same y value, whatever that y value is. So that would make it not a one-to-one function, okay? And the horizontal line test will actually show that. So if every horizontal line intersects the graph of a function in at most one point, then it's one-to-one. And notice here, both of them pass the vertical line test. So they're both functions, but the left is one-to-one and the right is not one-to-one. Because again, there's two points pretty much almost everywhere. Actually, if I go here, there's 3 points. Here, there's 3 points. So this is not a one-to-one function, even though it is a function. So let's look at these. A, determine if each function is one-to-one. Well, A is a function, and it says it's a function, so we don't really have to look for that. But we can see that if we make a vertical line, that it passes through 2 points, which means it is not, and I'm just going to write it like this, one-to-one. Now on B, it is one-to-one because there's not really any place where our function, if I draw a horizontal line anywhere, it's only going through one point. So this is 1-to-1. Okay. And that's really all we need to know about 1-to-1. But it's important because when we start talking about inverse functions, our functions that we're using for inverses have to be 1-to-1. So let's begin. Let f be a 1-to-1 function. Notice it's starting out saying that it's a 1-to-1 function. Because if it's not, then all bets are off, okay? So with domain A and range B. So I want to explain this picture. Usually I draw pictures similar to this. So instead of drawing it myself, I figure I'll use this, but let's look at what this is saying. So we have this circle on the left, and that's my domain, okay? So we're only going to talk about the actual function, the pink part on the top. If I pick a value of A and I go through some function, whatever the function is, and I get to B, then that's my range. The function is just whatever it is. It could be the square root. It could be something squared. It could be, what else have we, what other kind of functions do we, absolute value, right? Any of these are functions. So what we want to make sure of is that if we start in A, then we go through our function and we get to B, that's our range. And that's what we've been doing. And that's really, I don't think, maybe it's a little confusing because of the picture, but it's really what we've always done. Okay, we take a value from X, we make it go through some function, and we find a Y. Okay, so now what the inverse does is it actually can take us back to where we began. So now this is really the domain of the inverse. And if we go through the inverse function, and we'll see what the inverse of different functions are, but basically inverses of functions cancel functions. So, and I'll just quickly say the inverse of the square root is something squared, because that's how you get rid of a square root. The inverse of something squared is the square root, because that's how you find the value of what's inside, right? The absolute value is a little different, so I'm not gonna, actually, let's just take it off for now. So these are two functions that I'm sure you're very familiar with. And so basically, I can start at B and I go through an inverse and I can get back into the same value that I began with. Okay, that's the goal, but it only works if it's 1-to-1. Let me give you an example of why it doesn't work if it's not 1-to-1. So let's use squared and square root. Okay, so let's say we go through the top function and whatever A is, so we're going to square it. So this is, so f of x is equal to a squared, because a is the value we're picking. Okay, so let's say we pick 2. Okay, we go through our function, we square it, and we get 4. And the inverse of squared is, and I know you don't know this yet, but you'll see, is equal to the square root of b. So I come back, come back through, I take the square root of 4, I get 2, and I come back to exactly where I am. Okay, now remember, squared looks like this. It's a parabola, right? So is this a 1-to-1 function? No, it's not. So let's see what happens if I try to use a function that's not 1-to-1. Well, it worked for that one. Let's try to plug in, because let's say this is 2. It should also work for -2, right? So I plug in a -2 and I square it. I get 4. I take the square root of 4 and I don't come back to -2. I actually would come back to a different value, which is 2. Now, that's the problem, because what we want the inverse to do is bring us back to exactly where we started. It's like imagine you're leaving little breadcrumb trails on your way somewhere so you don't get lost. And then when you just follow the breadcrumbs back to where you began. That's basically what the inverse function does. And you can see if it's not one-to-one, then it won't work. So, right? Now, I don't think we get into this in this class, but there are ways that I can make this function into a one-to-one function. All I have to do is say, okay, well, let's say f of x equals x squared, but we're also going to add x is greater than or equal to 0. Now I only have one side of it, and now it is a one-to-one function. So that's kind of what we'll be talking about. I know that I think the rest of the problems are a lot of just doing some algebra, so I wanted to give a pretty complete explanation here. Hopefully that helps. Okay, so here's exactly what it's saying. So we did composition in 3.5. So what this is saying that is if I take the composition of a function with its inverse, and it's a one-to-one function, then notice how here the function with the inverse cancel. That's why when you take the square root of something and then you square it, the functions cancel. It's also true in reverse, which we've seen, right? If we have x squared, then we take the square root of both sides, and again, the functions cancel. It doesn't matter which one you do first, but it's always true. And the other thing that this is saying, which is very important, is that the domain of the inverse, and that's not what this is saying. There was something I wanted to say that it's not saying. I don't know if it's going to come up in a later slide, but let me say it right now. When you have inverse functions, the domain of the function f of x is equal to the range of the inverse function. And I don't know that you've seen inverse function notation before. So this is inverse function notation. That means I read this as the inverse of f, or f inverse of x. Okay, this is not, so let me write clearly down here. F inverse of x does not equal 1 over f of x. That's not what it means. Okay, if I wanted to write 1 over f of x in exponent notation, I would say f of x to the -1 power. Okay, that's true. But when you put that -1 next to the f, it means inverse. So it means we're looking for the inverse. So let's go back here. So the domain of the function f of x is equal to the range of the inverse, and the same thing vice versa. The range of the function f of x is equal to the domain of the inverse. So basically, domains and range swap, okay? That's kind of in a nutshell what we need. So first thing we're going to do is show how these are inverses. And there are steps that you need to take to find the inverse of a function, right? So first thing we're going to do is and we're going to use this cancellation property. So first thing we're going to do is we're going to say, we want to make sure that f of, wait, let me write it first differently. I want to make sure that if I take the composition of these two functions, which is the same as saying f of g of x, if that, well, let's just say that should equal, this needs to equal x. But if you get this to be true, also the opposite has to be true. So we have to be able to go both ways. So that means that this has to also be true. Okay? If one of these is not x, then it's not true. Now, I have seen people decide that they don't like this way of doing it, so they plug in a 1. That's not x. It may work for 1 and it may not work for 2. So I'm talking about you have to get an answer of x and they both have to be x. It's not that they have to match. If you get negative x for 1, that means they're not inverses. So even if both of them say negative x and you say, oh, well, they're equal, they must be inverses. No, I want to clearly state they have to come out to be x. Okay. So since I've written all over this slide, let's get a new one. Okay, so now here's what we're going to, oh, sorry. Where am I here? Okay, so let's start. So we're going to first do f composed with g of x, which is equal to f of g of x. So I'm going to, so what I'm going to do here is I'm going to plug in g of x to my f of x, into where g of x is. So actually, let me use different colors here. I think that may help some people. So this is g of x. So now I have f of g of x. Right? So I replace g of x where g of x is. And now I plug this into my f function. So this is equal to 3x over 1 minus 2x over, because I'm replacing all my x's. Okay, let me do this in blue, sorry. So everywhere there's an x, I'm now putting in 3x over 1 minus 2x. And then in the denominator, I have 2 times x plus 3. And where there's an x, I'm going to plug in 3x over 1 minus 2x. Okay, so I know this is even more complicated than you want it to be because these are two fractions. Sometimes you find they'll be easier, but I'm going to do a much harder problem here just because I want to show you. All right, so first thing I'm going to do is I want it, so I have just a fraction in the numerator, so I'm going to say that's fine. I'll just leave that alone. But in the denominator, I'm going to distribute and I get 6x. Yeah, it's okay, I can do it, right? 6x over 1 minus 2x plus 3. But I need to combine these two terms into one. So I'm going to multiply this one by the denominator, which gives me a common denominator. Okay, so now I have a common denominator. Next step, I have 3x over 1 minus 2x divided by, and this is in the numerator, divided by 6x plus 3 times 1 minus 2x all over 1 minus 2x. And now I have a fraction over a fraction. Well, actually, let's do one more thing before we do any more algebra. So the next step I want to do is I'm going to distribute out that numerator here. So I get 6x plus 3 minus 6x. Oh, that's interesting, right? Over 1 minus 2x. We can see that the 6x minus 6x cancel. And I'm going to end up with, I need another slide, sorry. All right, so let's see, I ended up here. So let's just grab, let's see, let me just grab that one piece. Oh, good. All right, so let's paste that here. And we'll continue from here. So this equals 3x over 1 minus 2x in the numerator divided by 3 over 1 minus 2x in the denominator, right? Which is equal to, now I'm going to do keep, change, flip. So this is 3x over 1 minus 2x times keep, change from division to multiplication, and flip the second fraction, right? And we can see now that this 1 minus 2x cancels with this 1 minus 2x. This 3 cancels with this 3, and I end up with just x, right? Everything else is gone. So check. So far, everything is going exactly as planned, okay? So I got my first part, and I need, so since I did f of g of x, now I have to do g composed with f of x, which is the same as g of f of x. And our functions are, let's grab these two functions. Okay, so, and I might as well get a new slide while I'm at it. All right, so let's begin. So we have g of, let's do colors. I don't know, colors always are helpful, I think. So now I have g of, and then I'm going to replace that f of x with f of x. So I have x over 2x plus 3. And now I plug that in everywhere I have an x. So this is equal to, well, g of x, so is equal to 3 times x divided by 1 minus 2 times x, right? But our x now is x divided by 2x plus 3. X divided by 2x plus 3. Okay? So let's try to simplify this a little bit. So I'm going to multiply the 3 into the numerator, and I get 3x over 2x plus 3 divided by 1 minus 2x over 2x plus 3. And again, I'm going to I would need a common denominator in the denominator. So I'm going to multiply this by 2x plus 3 over 2x plus 3. Okay? And now, again, let's grab that. Okay, and we'll begin from here. So we get 3x over 2x plus 3. That's again in the numerator, divided by, well, I have 2x plus 3 minus 2x divided by 2x plus 3. And let's simplify. So we get 3x over 2x plus 3 divided by, and notice now the 2x cancels with the 2x. So I just get 3 over 2x plus 3. And then I keep change flip. So I get 3x over 2x plus 3 times 2x plus 3 over 3. And then I can cancel. So the 2x plus 3 cancels with the 2x plus 3. The 3 cancels with the 3, and I end up with just x. So now, because when I compose f with g or g with f, I get x both times, I can conclude that f of x is equal to the inverse of g of x, and g of x is equal to the inverse of f of x, which means they're inverses of each other. Okay, so is there anything else it said? That's all we had to do. So I know it's a little bit of work, but that's basically how you show that the two functions are inverses of each other. Now, another interesting fact is that when you sketch the graph of the inverse, they are reflected around this y equal x line. So let me read, find the graph. Oh, I guess we should, well, find the graph of the inverse function, of the inverse of a one-to-one function by interchanging the coordinates of each ordered pair that lies on the graph of f. The graph of the inverse is the reflection of the graph of the function about the line y equal x, which means they're reflecting around y equals x. So if this is my original function and I have a comma b, then I know for my inverse function, notice how I have b comma a. I've already said before, the domains and range of these inverse functions switch. And the same thing is happening for the x cubed, okay? So, and also you can notice that where, this happens, this is kind of nice, where x equals y, because remember we're flipping it around y equals x, it's always got to hit that point that on that y equal x line. Okay, so these are the three places that y equal x line is going through, those 3 points, because x and y are equal. Okay, and sometimes it's kind of easy to find those points where they are on the graph, on the line. It's easier to see how it flips sometimes. So let's see what it says. Sketch the graph of f of x equals x squared plus 1 and its inverse. Also state the domain and range of the function and the inverse. So again, we know from section 3.4, I believe. Yeah, I think it was 3.4 where we did transformations. So sketch the graph of x squared plus 1. That is, 1 is outside of the function. So I have a parabola basically shifted up 1. So if this is 1, here's my parabola. Okay. uh-oh, we have a problem, don't we? What's the problem? It's not a one-to-one function. And I've already said that it has to be a one-to-one function. And let me just show you real quick why it has to be, and then I'll continue on. I'll probably have to erase everything. So let's say our one-to-one function reflects around that line, right? So that means that my point here, which is 0, 1, becomes 1, 0, right? So if goes to here. And that's my vertex. So from there, basically, I'm going to do something similar to this, right? Well, does anybody notice a problem now? If you don't notice a problem, we've taken something that is a function, which is x squared, and we've turned it into something that's not a function, because that blue does not pass the vertical line test. So because of that, what we have to do is we have to say, this doesn't work. First, we have to do what I said. Actually, I think I already talked about this a little bit, but we'll talk about it again. So we have to what's called restrict the domain, okay? Because now it's a one-to-one function. And I usually take the positive half if I can. It's usually the easier one. You could, yes, some people ask me, can you do the other side? Yes, you can do either side, okay? As long as it's one-to-one, you can take the inverse. So let's begin. Sketch the graph of this function. So we did. Now, where's the inverse going to be? Well, if this point again here is 0, 1, then we pick a point here, 1, 0. And that's our beginning, right? And then it's going to, the problem is that line is not very good. So first let me draw them and then I'll put the line in. I think that's probably the easiest way. So what I'm going to do is reflect it, and it's going to look something like that. And then here, let me put my y equal, this is my y equal x line. And we can see this is reflected around the y equal x line, okay? So we're switching the domain and range. And I don't know if you've noticed, but there's this, the red is the squared function, and we'll find out shortly that the blue line is actually the square root, and it has that shape that the square root has. So first thing I have to do is I have to say, well, for the function for f of x, right? If I want to know what my domain and range are, well, my domain I can see is the red line, and that goes from 0 to infinity, right? And it does include 0. And my range, well, that's my y values. It's starting at 1, and it includes 1, and it goes to infinity. Okay. Now let's look at our inverse function. So our domain, well, our domain starts at 1 and goes to infinity. Starts at 1 and keeps going on forever, right? This is our inverse function. So our range is going to be from 0 to infinity. Okay, because we're starting again, y equals 0, and we're going to infinity. And notice, just also notice, the domain of one is equal to the range of the other, and the range of the first one is equal to the domain of the second one. And again, this is always going to be true. So let's see, did I do everything? So I sketched the graph, yes. And its inverse, yes. And I stated the domain and range of both the functions. So that's basically what happens with inverse functions. Sketch the graph of, oh, I didn't really want you, so hold on a sec. Oh, I see. So this is great, because they took the opposite side. So now you can see how the opposite side also works. Perfect. So now notice they restricted their domain from negative infinity to 0, where we restricted our domain from 0 to infinity, right? Same graph, only they're taking the negative half. So this is actually perfect. And so if I do that, if I reflect around y equals x, I get this other function down here, the red one. And I can see that the domain of the function is from negative infinity to 0, right? And the range is from 1 to infinity. And then if I look at this other graph, I can see that the domain starts at 1 and goes to infinity, and the range starts at negative infinity and goes to 0 because it's coming up from the bottom, right? So again, now this is perfect because I showed you this way, which is the way I would think to do it. And here's the way they did it. Both ways are correct because I started with a one-to-one function. Okay, so how do you find the inverse of a one-to-one function? This is basically the steps. So change f of x to y, just because it's easier to work with. Then we exchange or interchange x and y, solve for y, and change y back to the inverse. And I'll show you exactly what that means. So we'll start with this function. These are actually a little bit more difficult, the rational functions, which I'm glad I'm doing because it is helpful. So if I want to find the inverse of a function, step 1 is I change f of x to y. So when I do that, I just get y equals 2x over 1 minus 5x, right? Done. Okay, second step, I interchange. They say interchange, I usually say exchange. Interchange or exchange x and y. What that means is wherever there's a y, it becomes an x, and wherever there's an x, it becomes a y. Okay. Third step, solve for y. Now, this is really one of the harder of the problems, but so I'm going to show you how to do this one. The other ones should come pretty much are much simpler if they're not rational functions. Okay, so let me show you how to solve for y. I think I'll start on a new page. And we'll put this solve for y. All right, so now we're going to solve for y. And what that means is I want to get all the y's on one side and everything else on the other side. So first I'm going to start by multiplying both sides by 1 minus 5y. Because it's too hard to work with the denominator, right? So that will cancel that, and I end up with 1 minus 5y times x is equal to 2y. And if I distribute, I get I get x minus 5xy equals 2y. So now I'm going to get all my y's on one side because I'm solving for y. Okay, and I have a y over here and I don't want it over there. So I'm going to add plus 5xy to both sides. okay? So I end up now with x is equal to 2y plus 5xy. Uh-oh, I have a problem. I have an x on the right-hand side, but it's not a giant problem because I can factor a y out of the right side, right? If I want to factor that, I can take out a y and I end up with 2 plus 5x. Okay. And now I really have that y kind of by itself. All I have to do is divide both sides by 2 plus 5x. And so now I have, and I'm going to swap them. So I'm going to just say y is equal to x over 2 plus 5x, right? So that is, I solved for y. And the last step is, this is the hardest step, is solving for y. But usually it's not that difficult, okay? So last thing I do is I change y to f inverse of x. And so now my final answer is f inverse of x is equal to x over 2 plus 5x. And now I found the inverse of the original equation, which is 2 over 1 minus 5x, and I'll write above it x over 2 plus 5x. Okay, so just checking, yes. So these functions are inverses of each other. Notice they're not reciprocals of each other. Remember, we said that that notation means inverse. It doesn't mean one. It doesn't mean like x to the minus 1 is 1 over x. It's actually notation for the inverse function. Okay, and that's basically how you solve them. Let me see. Let me pick. I'm actually gonna. I think I want to do another problem. Hold on. Let me. I'm gonna pause you guys for a second so I can find a good problem. Okay, I think this will make my point. So we want to find the inverse of f of x, or f inverse of x. F of x, find inverse. Okay, so step 1, we change f of x to y. So I get y equals x squared plus 5. Second step, I exchange x and y. So I get x equals y squared plus 5. Third step, solve for y. So solving for y, I get x minus 5 equals y squared. Okay, so now notice if I take the square root of both sides, which is what I'm going to do, right? Then I'll have y equals, actually I would have plus or minus. I would normally have plus or minus here, right? But we can't have plus or minus because that would make it not 1 to 1. So I just pick 1. I'm going to just leave off the sign, and I can say that the inverse, so that I can say that y equals the square root of x minus 5. And then step 4, I change the y to f inverse of x, and I get f inverse of x equals the square root of x minus 5. I could also get negative the square root of x minus 5, but I wouldn't choose that. But either way is true, okay? And let's graph it just so you can see while we're at it. So if I want to graph x squared plus 5, I know it's just a parabola shifting up 5, right? So there's my parabola shifting up 5. but I didn't restrict the domain, which I should have. So what I needed to say here is, let's make sure that X is greater than or equal to 0. And if I do that, then I get rid of that side. And then I don't have to worry about my plus or minus, right? Because I already know X is greater than or equal to 0. Now, so we have this point here, 0, 5, which means I'm going to have a point 5, 0 here. So this is 5, 0, and there's my point, right? So I'm starting here. And let's actually get a couple of points. So when, let's see, how am I going to do this? So let's do a little table. So here's f of x. And here's f inverse of x. And actually, hold on, let me do this. I need an xy, right? And then I need also an f inverse of x. So for my original function, when x is 0, f of x is 5. When x is 1, f of x is 6. When x is 2, f of x is 9. And I'm going to stop there because I just don't need it to get any bigger, right? So now for my inverse, remember, this is really like an ordered pair. So they're swapping. So I get 5, 0, 6, 1, 9, 2. And I'm going to have to extend this out. So I already plotted 5, 0, 6, 7, 8, 9. And if I have 6, 1, 7, 8, 9, I have 9, 2. And so that's my graph. I know that it's hard to tell. So that's my graph of the inverse function. So this is f inverse of x. This is f of x. And they both are symmetric or reflect around this y equal x line. And you can kind of see if I was more to scale, that it would, they kind of have the same shape. So they are inverses of each other. And I think the ones that you'll have to do are much more like this. That was, the first one is the most complicated, which is good because in case you see something that's complicated, you won't get scared. You'll understand how to do it. But here's more likely the kind of situations you'll see. And if you use the cancellation property, you'll also find that that they're inverses. If you compose f of g and g of f, you'll find that they're inverses. So that concludes this discussion of one-to-one and inverse functions. So have a good one, and I'll have another one for you soon.